Okay, and let me share my screen with you. Just a moment. Okay, perfect. So, okay, in the last class, we finished our class discussing about the Arctic horizon. And the Arctic horizon is that horizon that presents a higher content of clay in comparison with the surface horizon or the overlying horizon. And this higher clay content in the subsurface horizon is associated with clay alluviation or migration of clay from the surface to the subsurface horizon due to the migration of water, which carry clay from this area and forms and creates a clayic horizon. We also can see the Arctic horizon associated to clay elutriation, that is the loss of clay in the surface horizon because the runoff in semi-arid and arid regions, it's quite common that we have a lot of runoff because we don't have so dense vegetation cover, and the water penetration, the water infiltration through the soil is not so high, so the high runoff start to reduce the content of clay particles in the surface, and so creates a gradient of texture, a clay gradient between the surface and the subsurface horizon. We also can see the Arctic horizon related to the clay formation in the subsurface horizon because the weathering and leaching, they produce higher content of clay in the subsurface horizon. We also can see the clay destruction, especially in wet regions and acidic pH soils that has an intense destroying of the clay, destruction of clay, and the reducing of the clay content in the surface horizon, or the upward movement of coarse bodies that, because the bioturbation tends to be concentrated in the surface horizon. So we create this difference of texture between a coarse texture surface horizon and a clayic texture horizon, and they have different colors, different conditions to influence of water penetration and percolation, CEC, and several other physical chemical properties. The Arctic horizon possess some diagnostic criteria, and the first one is that it's a mineral material, so the organic carbon content should be lower than 20%. So even you found in the field some horizon that present a higher content of clay in the subsurface, but it present also a high content of organic carbon, like equal or higher than 20%. It's not an Arctic horizon, should be other thing. Even it present a higher content of clay in the subsurface horizon. Okay, so beyond the low content of organic carbon, it should present a texture class of loam sand or thinner and at least 8% of clay content. Why? Well, we are discussing about a soil horizon that accumulates clay. So of course, it shouldn't present a sandy texture like sand or loam sander. So we should present a loam sand or thinner. And of course, it should present at least 8%. If you have a horizon that has less than 8%, like 5 or 2%, maybe is not a concentration of clay, it's just a residue of clay that you can find in that horizon. Okay, so at least 8% in the clay content, and it should present at least a texture of loam sand or finer in the texture triangle. Beyond this information, you should present a variation of texture and comparison between the overlaying texture and overlaying coursing texture and the arctic horizon. Okay, the coarser texture layer shouldn't be separated from the arctic horizon by a lithic discontinuity. What is a lithic discontinuity? Is this: the lithic discontinuity is a property, is a criteria, is a diagnostic criteria that we use to identify some soils that was formed by alluvium or and colluvium materials. In this picture, we can easily see several colors and layers that are related to alluvial fans. So this soil was formed very close to the river, and river help the formation of each of these layers by the material that was deposited according to the energy of the river. When river has high energy, only coarse fragments and sand can be deposited, and maybe the color is not so dark because you don't have so much organic material, because in high energy rivers you just bring the material, organic material along. Organic material is low density material, so they couldn't deposit in energy and high energy rivers. But when the water is calm, the river is calm, you can register the sedimentation of clay, even silt, and lots of organic carbon, organic matter. So we can easily see several layers with different colors, but also different textures. And this clay layer, it's below a sandy layer. But this difference of texture shouldn't be used to identify an arctic horizon, because in this case, this difference of clay content, this difference of texture is not related to any of this process. It's not related to clay alluviation or deterioration, formation of or destruction, biological activity, or even an upward movement of coarse bodies. It's just a difference of texture that's related with difference energy of the erosion transporter. In this case, river, but we can found in sand that was transported by wind. We can think in colluvium that was eroded and transported by gravity. So if we have lithic discontinuity or change of color, texture, or even minerals that we can find that are related to colluvium, alluvium, or formation of terraces and fluvial plains, they are not a possible arctic horizon. This variation of texture and of clay content shouldn't be related to arctic horizon, but to a lithic discontinuity. So this difference of texture should be only related to one of these processes that we talk about. The coarser texture layer directly overlies the arctic horizon, but this surface layer does not form a plug layer or shouldn't be influenced or intensively influenced by man. So man did not create this coarser texture layer. Okay, It's not something that was created or selected or influenced by man activity. It's a natural process related to one of these processes that we talk about in the last slide. Okay? And the coarser texture layer that does not directly overlie the Arctic horizon. The distance between this coarser texture layer and the Arctic horizon should be higher than 15 centimeters. So we always should compare the Arctic horizon and the coarser texture layer in a distance up to 15 centimeters or equal or lower than 15 centimeters. Okay. For example, if I have a soil profile with an A horizon and a B horizon, or for example, an A horizon, an AB horizon, and a B horizon, and this AB horizon has more than 15 centimeters, I should use the difference of clay content between the B and this AB horizon. I can't use the A horizon because I should compare a variation of texture, a variation of clay content in a distance equal or lower than 15 centimeters. Okay? And this comparison between clay content in equal or lower than 15 centimeters should use this criteria, should follow these values. Okay, if the coarser texture layer has less than 15% of clay, the Arctic horizon should present at least 6% or more clay than the coarser texture layer. Okay, if the coarser texture layer has a clay content between 15 and 50% of clay, we should calculate a difference, a ratio between the clay content of the Arctic horizon and the coarser texture layer. And this ratio should be equal or higher than 1.4%. 1.4, I'm sorry, it's not percent. So if I calculate a ratio between the clay content of the Arctic horizon and the clay content of this coarser texture layer, this ratio should be equal or higher than 1.4. And if this coarser texture layer has more equal or more than 50% of clay, the Arctic horizon should present at least 20% more clay than this coarser texture layer. Okay, let's see some examples. Soil number 1, we have an A horizon between 0, the surface, and 10 centimeters of depth. So the A horizon presents 10 centimeters. This E horizon is between 10 and 35 centimeters of depth, so present 25 centimeters of thickness. And the B horizon starts at 35 centimeters and below. Okay. The clay content of the A horizon is 12%, 10% for E, and 25% for the B horizon. So let's see. The coarser texture layer, that in this case, the A horizon, present less than 50% of clay. In this case, the Arctic horizon should present at least 6% more in absolute term, more clay than the E horizon. So if the E horizon present 10% of clay, the B horizon should present at least 16% of clay to be classified as an Argec horizon. In this case, the B horizon presents 25%, much more than only 16. So in this case, this B horizon is an Argec horizon because it follows this criteria that if the coarser texture layer present less than 15, the Arctic horizon should present at least 6% more clay than the coarser texture. And the soil follows this criteria. So this B is an Argec B horizon. Okay, perfect. Let's see the example 2. In this case, we have an A horizon in between the surface and 25 centimeters, so present 25 centimeters of thickness. The BA horizon, it's between 25 and 30 centimeters, just 5 centimeters of depth, or of thickness, I'm sorry, just 5 centimeters of thickness. This B1, it's between 13 and 85 centimeters of depth, so present 55 centimeters of thickness, and the B2 starts on 85 centimeters and below. Okay, let's see the clay content of each one. The A horizon present 42% of clay content. The BA 55%, the B1 65%, and B2 70% of clay. Okay, let's see the coarser horizon. In this case is the A horizon, and the horizon with the highest content of clay is the B2 horizon. We can't, or we shouldn't compare the clay content of B2 and A, because the distance between them, it's higher than only 15 centimeters. The A horizon ends at 25, and the B2 only starts at 85. So we have 16 centimeters of distance between them. That's higher than 15, so we shouldn't compare the B2 and A. Okay, let's see the B1. The B1 presents 65% of clay, and the distance between B1 and A is only 5 centimeters. That's the thickness of the BA. So I can compare the clay content of B1 and A horizons. So let's do that. The A horizon presents 42% of clay. Let's see. 42, it's higher than 15, but it's below 50% of clay. So in this case, the ratio of clay content between the Arctic horizon and this coarser texture layer should be equal or higher than 1.4. So let's calculate the ratio. It's quite easy. The B1 clay content is 65, and the clay content of the A horizon is 42. And in this case, in this specific case, the ratio is 1.5. 1.5 higher than 1.4. So in this case, the soil 2, it's also present an Arctic horizon, because B1 horizon is an Arctic horizon. Okay, so again, we follow the criteria to identify an Arctic horizon in the soil 2. Let's see the soil 3, the 30 example. In this case, we have the same clay content, and I just changed the thickness of the BA horizon. This transitional horizon now has 13 centimeters of thickness. It starts at 25 and ends at 55, so 30 centimeters of thickness. In this case, I can't compare anymore the B1 horizon and the A horizon. I should compare BA and A because the distance between B1 and A is higher than only 15 centimeters. Now I should compare the clay content of BA horizon and A horizon. So let's calculate again. The BA horizon have 55% of clay content and the horizon 42. So we have a ratio of 1.3%, 1.3. This ratio is lower than 1.4. So in this case, the soil number 3 did not present a RGEC horizon. But JJ, we could see the clay content, it's increasing here. Okay, I agree with you. But it's not following the diagnostic criteria. So, however, the clay content is increasing with depth, it did not follow the diagnostic criteria to identify an article horizon. In this case, okay, we will see that we have other diagnostic criteria that could identify an article horizon, but following the increase of clay content, it's not following the necessary increase to identify an arctic horizon, okay? And let's see the soil number 4, that we have an A horizon between the surface and 25 centimeters. We have a B1 horizon between 25 and 6 and 5, I'm sorry, 5 centimeters. So have 25 centimeters of thickness. We have a B2 between 50 and 85, 35% or 35 centimeters of thickness. And the B3, it's 85 and below. The A horizon presents 52% of clay content. The B1 60, the B2 65, and the B3 7. We can compare the B3 and A again because the distance between them is very, very higher than only 15 centimeters. The B2, we also can compare because the distance is 25 centimeter. And so we should compare the B1 and A horizon. And in this case, 60, we should calculate the ratio between 60 and 52. Let's see. If we have more than 50% of clay or half of percent of clay, the Arctic horizon should present at least 20% more clay than the coarse texture layer. So in this case, we have an A horizon that presents 52% of clay, and to identify an Arctic horizon, we should present on B horizon that has at least 72%. That's at least 20% more clay than the A horizon. So in this specific case, the soil number 4 also it's not did not present an Arctic horizon because we don't have the increase of clay content necessary to identify the Arctic horizon. Okay, so you can see that
Okay.
number 1 and number 2, they follow the criteria to identify an Arctic horizon, and 3 and 4, they did not follow.
So,
Okay,
okay.
perfect, perfect. Beyond the clay content, we also can looking for other morphological features that could identify Arctic horizon. Okay, some of them are alluvial clay features. And the alluvial clay features you saw in the class of paleopedology, we can see clay bridges that connect at least 15% of the sand grains. So we can see like this, the coarse material, the sand grains, they are connected by clay coatings. And these clay films, these clay coatings also help us to identify this horizon as an argic horizon. Even it did not follow the minimum of the clay content increase to identify an argic horizon if it presents a higher content of 15% of clay coatings, we can identify as an argic horizon, okay? We also can see the argic horizon if it presents clay coatings, which are, oh, sorry, this clay coatings are this clay surface shiny, this shiny clay surface that we can see that represents clay eluviation, that represents migration of clay. So even the clay content increase, did not follow the diagnostic criteria to identify an argic horizon if you can see these clay coatings covering the surface of the pads of the aggregates, these shiny surfaces, you can identify an argic horizon, okay? We also can see in thin sections some materials that represent the clay migration, like, oh, I'm sorry, in this case, if we see fillings or coatings of clay in these materials, they represent to us clay eluviation, clay migration, because these infillings, they represent clay migration, clay particles that migrate through the soil inside the voids and start to deposit, to start to sedimentate, start to precipitate over the walls, on the walls, and they start to infilling the voids, the pores with these clayic materials. So even if we didn't not follow the clay increased content to identify an argic horizon, but in thin sections in the lab, we could identify a higher quantity of infillings and clay coatings, we could identify that horizon as an argic horizon. Okay?
Okay.
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 Okay. And if we calculate a ratio between the fine clay and total clay contents, and this ratio it's equal or higher than 1.2%, we also could identify the argic horizon, okay? Of course, it should compare with the overlaying coarse texture. We always should compare the argic horizon and this coarser texture layer in the surface or overlying the argic horizon. This ratio should be equal or higher, 1.2% higher, okay? We also have a nidec horizon, and the nidec horizon, it's quite similar to argic horizon because it's a clay-rich subsurface horizon too, but in this case, the nidec horizon did not present an increase of clay content. So all the soil profile, all the horizons present similar clay content, okay? So you can see an argic, a clayic horizon, but the clay content it's quite the same or even similar, or it's not high enough to identify an object horizon. Okay, and the nidec horizon should present a strong grade, should present several aggregates or pads. So the high content of clay here help or favor the formation of pads or aggregates. And we can see at least 90% of the fine particles, the primary particles, the material that is composed by sand, silt, and clay, they are usually together, grouping as pads or aggregates. We didn't see a lot of material that's is poorly distributed, or it's not aggregated, or it's not grouped as aggregates. It's not a powder material. They all they are all aggregates. They are all composing or forming aggregates. Okay, and we can see easily a lot of shiny faces. So is a clayc material, it's a clayc soil with all the horizons present similar texture, and this clay texture helps the formation of a strong grade and at the same time produces shiny faces. These shiny faces are formed by the expansion and retraction of the material. It's a process that we call shrink and shelling process, the expansion and retraction of the material according to the content of water in the soil. So in the wet season, the soil is wet and the clay fraction expand, and during the dry season, the clay fraction retract, and this change the volume of the soil. And during when the wet season, when the material expanding, it's changing, it's increasing its volume, we can see the material be compressed between the aggregates. So one aggregate is compressed or pressured against each other. So this compression produce some shiny faces that we call pressure faces. The nidec horizon, it's usually related to materials that it's easily weathered and produce a lot of clay, like mafic igneous rocks, like basalt and diabase and gabbro. They usually easily could be weathered and produce a lot of clay. On the other hand, we don't or we can't see a nidec horizon that's formed by the weathering of a sandstone or granite, some material that can't produce clayic materials, clayic horizons, or could produce a lot of sand. Okay, so you can't find a nidec horizon in a soil formed from the weathering of a sandstone, a quartzite, a banded iron formation. It's not common to see that because these materials has a lot of quartz, has a lot of sand, will produce sandy soils or soils with a lot of sand, and we can't see the nidec horizon in these cases because the nidec horizon should be related to a soil that possesses a lot of clayic horizons. And the nidec horizon did not present a high difference between the clay content with the horizons that are above. Okay? Here are some examples of these shiny faces in these materials that present a strong grade. So you can see in my hand that we only have pads, we only have aggregates. We can't see a powder material, dust material in my hand. It's just aggregates. And the diagnostic criteria to identify a nidec horizon is First of all, it's also a mineral material, so the organic matter content, organic carbon content, I'm sorry, the organic carbon content should be lower than 20%. So we can't find a needing horizon with 20% or more, like 30, 40% of organic carbon. It should be lower than that. Okay? And it should present at least 30% of clay, so should present a clay texture. We can't see a native horizon associated with a loamic texture or a sandy texture or siltic texture. We can't see that. Okay, and should present a combination of one of these possibilities. Okay, first of all, a moderate to strong grade with with a type of structure that it's angular block or subangular block. Okay, and this material should break into polyhedral or flat-edged second level structure with pressure faces, these shine surfaces, okay? In at least 20%, 25%, I'm sorry, 25% of the material, okay? So we should present a moderate to strong angular structure following a block structure, and this block structure should break in a polyhedral or flat-edged second level structure. Or it should present a polyhedral structure with these shine surfaces and did not present a block structure. Okay, so the nidec horizon couldn't be related to a granular structure or platy structure or prismatic structure. All the other structures, all the other shapes and types couldn't be identified in the nidec horizon because it should present this specific kind of structure, polyhedral or angular and subangular block. And of course, present a moderate to strong grades. Okay. Beyond that, it should present a high content of iron extracted by ditronite and oxalite. These extracts, they represent iron, free iron and activity iron. This free iron is related to all iron oxides in the soil. And this iron extracted by oxalite, it's associated to poorly crystalline minerals. So we should present a high content of iron associated to oxides in the nidec horizon. It's because the nidec horizon should present a high content of clay and oxides, iron oxides, they generally compose this fraction, the clay fraction. So we should present a soil that possesses a lot of clay, I'm sorry, and at the same time present a high content of iron that's express a high content of iron oxides. Okay, and of course we should present a higher content of iron associated with oxalite than ditronite. Okay, we don't have in the nidec horizon any evidence of a plintic horizon. We did not talk about then the plintic horizon, but the plintic horizon is an horizon that possesses mottles, concretions, or nodules of iron and or manganese. So the nidec horizon shouldn't present mottles, concretions, or nodules, okay? And it's because these conditions, these features are related to a variation of the water table level, and the nidec horizon is formed in in well-drained soils, in soils that we don't have stagnant water or influence of water table level. So we can see something that could be related to water table level in the nadic horizon. And this nadic horizon should present a thickness of at least 13 centimeters. So 30 centimeters of thickness. Okay, so if I present if I follow all these criterias, but the thickness is only 10 centimeters or 15 centimeters, it's not a nadic horizon. It should present all these diagnostic criteria. All of them should be followed. Okay.
Okay.
Other, oh, perfect, perfect. Other horizon that's quite interesting and is related to alluvial migration, like the Arctic horizon, is the Spodic horizon. The Spodic horizon is a horizon that's formed by alluviation of clay. And you can say, JJ, we saw that in the Arctic horizon. Okay, I agree with you. But the Spodic horizon express the migration of organic matter and iron oxides and aluminum oxides. So the Spodic horizon is not a migration of clay minerals like kaolinite or alloysite or other aluminum silicates or minerals with silica. In this case, we have the migration of organic matter and or iron and aluminum. Okay, like in this picture, we can easily see between the surface and 10 centimeters of depth. Here is a horizon because this dark color is not so dark. I agree with you, but it's a dark color. So this is an A horizon. Okay, let me use the pointer. So here is an A horizon, and this white zone, this white layer, this white horizon, it's an E horizon. And below the E horizon, we have again a dark color. And below that, we have a darker color, the darkest color that we can see in this picture. And this horizon, these two dark colors, they are P horizons, because here the organic matter is not accumulated by the littering or the deposition of material in the surface. But here, and especially here, the organic matter is concentrated, it's accumulated by migration of organic matter from the surface horizon to here, especially here. So the organic matter migrates from the surface horizon and from the E horizon to these two subsurface horizon and comprehend and compose and create the spodic horizon. A horizon that's composed by organic matter that migrates from the surface to the subsurface. Okay? The formation of the spodic horizon is very interesting because it's related to soils that possess a sandy texture. So it's quite common to see spodic horizons in the coast because generally you can see sandy soils there, and this sandy texture couldn't preserve organic matter. And when you have a lot of rain in these coastal areas, the rain migrates through the soil and brings and carries the organic matter from the surface to the subsurface horizon. And generally, the water stop its migration when water found the water table level. So the spotted horizon, it marks an ancient water table level. In this case, if I collect a sample here and if I date this material, like, oh, this material has 30,000 of years before the present, I know that in the past, at 30,000 of years before the present, this was the position of the water table level. Nowadays, of course, the water table level migrates to a down position. Okay, so the spotted horizon marks when or where water stop its migration and help the concentration to accumulation of organic matter. And this accumulation of organic matter creates the spotted horizon. In this case, we have two spotted horizons. This first, that's between 20 and something like 45 centimeters of depth. And this horizon that starts at 45 and ends like something like 80 centimeters. We have some tongues here, but let's see the average. Okay, it's something like 80 centimeters. So we have this horizon and this horizon. They both are spotted horizons. Probably this one, it's younger than this because this lose a lot of color. So maybe the organic matter that in the past was concentrated here just migrate from here to here. So here is the oldest and is the youngest. And maybe today we have another spotted horizon that's created below this surface and it's younger than that. It's quite common to find several spotted horizons in these materials. When we dig a huge hole, we can see several spotted horizons, and they generally mark several age, different ages. And we could relate these different ages with the position of the water table level in the past, of course. And if we found today the water table level today, we can identify when the water table achieved that depth, achieved that position. Okay. It's quite common to find in these cases this dark color, but we also can see a yellow color or a dark yellow color that show us the migration of iron oxides in this condition. We can see this. So we have this A horizon here, this dark, not so dark, but it's a dark horizon. Here this white horizon, this A horizon. In here, we can see again a dark color, red and brownish color, and here we can see yellow color. So here, organic matter was deposited. We have alluvial organic matter, and here we have alluvial oxides, probably iron oxides. The spotted horizon, it also presents some diagnostic criteria that should be followed. The first one, it's the presence of mineral material. So even when the spotted horizon accumulate a lot of organic matter, the organic matter content of, or the content of organic carbon should be lower than 20%. Okay, if I see a horizon in the subsurface that present a higher or equal content of organic carbon.
This screen, your screen.
My screen stopped. Oh, let me check just a moment.
Okay.
Oh, no.
I'm seeing it.
You can see my screen now?
I can see it now.
Okay. So even we found something like this with subsurface horizon with dark colors. If the organic carbon content is higher or equal or higher than 20%, we have an organic horizon, and in this case is a folic or histic horizon. It's not a spodic horizon, okay? Because folic and histic horizon present at least 20% of organic carbon. So the spodic horizon always present lower than 20%. The age of the spodic horizon should present low values because the spodic horizon is associated to acidic environments, environments that we have a lot of water, available water to migrate the organic matter from the surface to the subsurface, okay? Or we have some materials, organic materials that has a high content of lignin, and to the destruction of this material, the microorganisms yields a lot of acids, and these acids decrease the clay content of the material, and after that the organic matter start to migrate, and of course the acidic pH will be achieved by the high rainfall regime or because the production of acid due to the weathering, the destruction of these lignin-rich materials, the lignin-rich organic materials, okay? Of course, this pH will be achieved if the soil is not fertilized or limit, okay? But in general, we found spodic horizons with low pH, moderate to extreme acid. We should present a high content of aluminum extractable by oxalate should be equal or higher, at least 1.5 times equal or higher than the material above this spodic horizon, okay? It should present in 1 centimeters, at least 1 centimeter, organic carbon equal or higher than 0.5% and a high chroma, okay? Because this material possess a strong color with high chromas, okay? And if one of the subhorizons it's present at least one of these colors, a hue of 5YR or rather a hue of 7.5YR and a value equal or below 5, a hue 10YR and a value and a chroma equal or below 2, a hue of 10YR and a chroma equal or higher than 6. If you accumulate iron, it's common to see this specific case. A color of 10YR 3/1 if you concentrate organic materials, or a hue of neutral with gray colors and a value equal or below 2 if you concentrate organic materials, okay? So you can see the spodic horizon could present a very red color, a yellow color, gray colors, high values, low values, high chroma, low chroma. They could be very different between them, but they concentrate materials that migrate from the surface to the subsurface horizon. Beyond this, we have that it's an overlaying of cleric material that's not separated from the spotted horizon by a lithic discontinuity. Okay, so we have a cleric material, I'm sorry. And what is a cleric material? This is the E horizon material that possess a white color. So we have the contact between the E horizon, the cleric material, and the spotted horizon, and they are not separated by a lithic discontinuity. So this difference of texture, difference of color is not related to sedimentation of material. It's a pedogenetic process. It's a migration process. It's not only sedimentation of clayic material, organic matter, rich material, and sandy material. It's not something that was deposited by river. It's something that was created because the migration of clay. Okay, and if this material its overlayer, this horizon, okay, of if we have a transition horizon, this transition horizon has less than 1/10 or the overlaying cleric material. So we have an A horizon, an E horizon, and an AB horizon or a BA horizon. This transitional horizon shouldn't present a very thick, it's not very thick, or possess 1/10 or less than the thickness of the E horizon of the cleric material. Okay? If we present 10% of more of the sand grains, the structure of the sand grains of the horizon, it should present cracked coatings. So we can see if present loamic or siltic or a clay texture, it should present cracks in this material. And sometimes these cracks are fulfilled by clay or even sand materials from the surface horizon. Okay, it could present a subhorizon that's cemented, and the cementation is less weakly cemented in 15% or the half of the horizontal extension. So we can see the cementation of this material. Usually the cementations is composed by organic matter and iron. They form some metal, organic and metal ligations that produce the cementation of a horizon and produce a cemented horizon. Okay. Or we can see a subhorizon with a high content of aluminum and iron that's tractable by oxalate, and this is higher than these materials over the spotted horizon. This spotted horizon does not form a natric, limnic, or a testalic horizon. These horizons we will talk about then in the next classes, but they are related also to materials that possess a sandy texture or a high content of organic materials. But in this case, they are formation of organic material by incipient weathering of the L horizon. Okay, and this spotted horizon should present a thickness at least of 2.5 centimeters. So it's not so thick like the other horizons, it's at least 2.5. Okay, again, you shouldn't you shouldn't record all this information, but what you should comprehend that spotted horizons, those horizons that possess a concentration of organic, iron, and aluminum in a subsurface horizon to the elevation of these materials from the surface to the subsurface horizon. Okay, these details we can see, we can check in the book. We also have to talk about the Ferhalic horizon. The Ferhalic horizon is also a subsurface horizon, and the main property of it is a distinctive weathering, and so we can see the concentration of the products of the intense and deeply weathering. So the Ferhalic horizon, it presents a higher content of kaolinite, aloysite, gibbsite, hematite, goethite, materials that was produced by an intense and deep weathering. Okay, the Ferhalic horizon did not present any kind of high activity clay. So we can see here materials or clays that could be related to incipient weathering. So we can see here smectites, ilites, and other clays, clay fractions, clay minerals that could be expensive, that could expand or change its volume, it change its size according to its water content. Okay, so the Ferhalic horizon is composed by low activity clays, always, because the Ferhalic horizon is formed by intense and deep weathering and leaching. Okay, the Ferhalic horizon, it's usually related to well-drained soils, which formed iron and aluminum oxides and concentrate these materials. We can't see in the Ferhalic horizon, we can't see in this Ferhalic horizon a high volume of parent materials or fragments of the parent materials, or a high volume of minerals that could be easily weathered. So in the Ferhalic horizon, we can't find a huge or even a high volume of feldspars composing the coarse materials. We can't see a lot of fragments of rocks of the parent material, or we can't see sandy fraction that's composed by easily weathered materials like pyroxene, feldspar, plagioclase, other minerals that can be easily weathered. The coarse fraction, the sand fraction, is essentially composed by quartz. That's a hardly material that it's hardly weathered. So this Ferhalic horizon generally have the sand fraction composed only by quartz, and the clay fraction composed by iron, manganese, and aluminum oxides, and kaolinite and aloysite. And it's just this. Okay, they tend to be very thick, and we usually found them between the tropics, because it's there we can find a high precipitation, higher temperatures, and an intense activity of organisms, of termites, wormholes, and even the vegetation, which form the Ferhalic horizon. We can easily see several works, several studies that relate the formation and occurrence of Ferhalic horizons and biological activity, because they create and they form these aggregates that we can see in the Ferhalic horizon. Okay. Here is a picture that someone took it. Here's me. I have just 1.6 meters, so I'm not so tall, of course. But here we can see an example of a Ferhalic horizon. It starts below this dark horizon. Okay, this is one Ferhalic horizon that has more than 3 meters. Okay, and it's quite common to see this in the tropics. And you can think 3 meters of just one horizon. The Ferhalic horizon is a lot of meters. It's too thick when we compare with glacial soils, periglacial soils, or even temperate soils. Okay. Oh, here's a picture of the same soil profile, but we have a car here, so you can see the scale and try to figure out how thicker this soil is. Here in the bottom position, we didn't not found the sea horizon, so we use this wall to collect the samples, but we can't find the rock, even 6 meter of thickness. We have a soil here which has more than 6 meter of thickness. It's a lot of thickness. And here we have a rainforest fragment above this soil. Probably this rainforest is quite related to this soil because it storage a high quantity of water, and this water could help the survivor of this rainforest. Here, it's a poor soil. The chemical nutrition, the chemical content of nutrients low, but the liter and the reading helps a lot the nutrition of this rainforest. The diagnostic criteria to a Ferhalic horizon is not so much, but they are very important. First of all, as the others, we have a mineral material, so the organic carbon should be lower than 20%. So we can find a Ferhalic horizon with more or equal or more than 20% of organic carbon. Okay. Usually it has less than 1%. Usually the organic carbon is quite low, but okay. We have a texture class of sandy loam or thinner and at least 8% of clay. And the Ferhalic horizon concentrate clay, but did not concentrate clay by clay migration or clay alluviation or elutriation, but by clay formation. And the Ferhalic horizon possess content of clay very close to these horizons in the surface or the overlying horizon. So in the opposite of the Arctic horizon, the Ferhalic horizon possess a clay content that's very similar between all the horizons. It's like the Nedic horizon, but the difference between the Nedic horizon and the Ferhalic horizon is that the Nedic horizon should present shiny faces, and the Ferhalic horizon should not present shiny faces. So always the Nedic horizon is shining. It's why we said Nedic. Nedic means what? Shine. And Ferhalic, something that accumulate, that concentrate iron, and iron, it's opaque, did not shine, so the Ferhalic horizon did not shine, okay? It has less than 80% of the volume of the whole soil composed by coarse fragments or piezoplantic concretions or nodules or remnants of a petroclitic horizon. JJ, I'm not sure about what is a piezoplantic concretions or a petroclitic horizon. We will talk about them in the future, but they are just concretions. So the Ferhalic horizon did not present a high volume of coarse fragments or concretions or nodules, okay? This is very important. It has a low cationic exchange capacity. If we calculate a ratio between this cationic exchange capacity by the clay content. The ratio between the cationic exchange capacity and the clay, it's lower than 16 centimole per kilogram of clay. Okay, so the activity of clay should be low, should be very low. Let's see this. For example, we have this case on soil with a horizon. Just a moment. Okay. With a horizon, a B1 and B2 horizons. And here we have the content of calcium, magnesium, potassium. We can find sodium in this case, the content of aluminum and hydrogen. And here we can see the CEC, that's the cationic exchange capacity. Here we have the capacity. Here we have the clay content of each horizon. And here we need to calculate the ratio between the CEC and the clay content. Okay, so first of all, we have to calculate this. We have to calculate the CEC. We just need to sum calcium content, magnesium content, potassium content, and hydrogen content. Okay, aluminum we don't not use to calculate in this case because here this hydrogen it's already considered aluminum and hydrogen. Okay, so in this case to calculate CEC I just use hydrogen. So I just need to sum 0.4, 0.3, 0.1, and 1.9 to calculate to a horizon. The ferralic horizon is just a B horizon, so I just need to calculate to B1 and B2. Let's see this. Okay. So let's calculate. In the first case, we have 0.4 plus 0.3 plus 0.1 plus 1.2. So we have 2 centimole charge of kilogram of soil. And here, as the values are quite the same, just here it's different. We have 2.1. Okay. And we have the clay content here. And now we have to calculate the activity of the clays. So we just need to do this. 2 and 34. And multiply by 100. So here we have 8.3. And here probably we'll have a very similar result. Let's see, 2.1 and ratio between 22% and multiply by 100 and 9.5. 9.5. So in this case, we have values that are below 16. So in this case, the B1 and B2 follow the criteria to identify a ferralic horizon. They present a low activity clays, okay? And this both cases, B1 and B2, okay? Beyond this content of clay and the CEC, I should possess less than 10% of easily weathered minerals. As I said, I should not present a high volume, a high content of feldspar, pyroxene, plagioclase, and other minerals. I did not present endic or vitric properties. Endic and vitric properties, they are related to materials that was wafted from fresh or new fresh volcanic ash and volcanic materials. They possess olefins and other poorly crystalline minerals. Okay, so Ferhalic horizon did not present a high content of poorly crystalline minerals. In general, they present well crystalline minerals like goethite, hematite, and others, and should present a thickness of at least 13 centimeters. So 30 centimeters is the thickness, it's the minimal thickness of a Ferhalic horizon. As we can see, it should be very thick when we compare with other horizons, like the spotted horizon that we saw. It's just 2.5 of thickness, and here's 30. So it's a lot. It should be very thick to identify a Ferhalic horizon. Okay, so the Ferhalic horizon, it's a horizon that possesses a high thickness, did not present poorly crystalline minerals, did not present a high content of easily weathable minerals, present low activity clay, did not present a high volume of coarse fragments or concretions or nodules, and present at least 8% of clay or a sandy loam texture or thinner than that. Okay, this is the Ferhalic horizon. It's quite simple when we compare the other ones.
Okay.
Okay, so
Bye.
let's stop. I know that's a lot of information. It's always a lot of information when we talk about soil classification. But again, don't worry. You don't need to record all this information. You just need to remember, okay, what's the difference between the Ferhalic horizon and the Argic horizon? The Argic horizon possess some process that act and change the texture of the surface and the subsurface horizon. Okay, it's the Arctic horizon. The Ferhalic horizon did not possess this kind of process, so the texture of these horizons are the same or very similar between them. And the Ferhalic horizon needs to present low activity clays. The Arctic horizon could present high or low. Don't care. We don't care about that. Okay.
Okay.
Okay. So I will finish the class now. Okay. And in the next class, we will continue to discuss about the diagnostic horizons. We talk about the last ones, and after that, we could talk about the classification using WRB system. Okay.
Okay.
Okay. So Nedima, thank you very much for your attention and see you later. Bye-bye.
Bye bye.